In June 2010, a cybersecurity researcher named Sergey Ulasen was helping investigate a strange problem coming from Iran. Windows computers were crashing, rebooting, and then doing it again. What Ulasen and other researchers eventually uncovered was one of the most sophisticated pieces of malware ever discovered. Unlike most malware, it wasn't designed to steal passwords, money, or files. It had a much more ambitious objective: destroy machinery. This was Stuxnet, and it took months for researchers to uncover what it was built to destroy. Hi everybody, I'm Isa, today's host. This is Tech Stories Under 10 Minutes by DevStats. If you like these types of story times, make sure to subscribe and hit that like button. Once security companies started pulling Stuxnet apart, the first thing that stood out was how expensive it looked. Stuxnet used 4 previously unknown Windows vulnerabilities, known as 0 days, along with another already patched exploit. It could spread through USB drives and local networks, while stolen digital certificates from Realtek and J-Micron made parts of it look like trusted software. A single 0 day can be extremely valuable. Stuxnet had 4. Someone had invested serious resources into this thing. But what was all of that effort for? Because on most infected computers, Stuxnet did almost nothing. Instead, it was looking for one very specific piece of software: Siemens Step 7. Step 7 is software used to program PLCs, industrial computers that control physical equipment like motors, pumps, and valves. When Stuxnet found a computer running the right Siemens software, it positioned itself between the engineering workstation and the PLC. It could quietly inject its own instructions into legitimate code, then show the engineer a clean version when they checked what was running. Researchers still didn't know what physical system it was built to target, but another set of extremely specific conditions would reveal it. Stuxnet wasn't looking for just any industrial controller. It checked for frequency converters made by Vacon in Finland and Ferraropaya in Iran, operating between roughly 807 and 1210 Hz. Those unusually high frequencies were an important clue. Drives operating in this range can be used to run gas centrifuges. These machines spin at extreme speeds to separate uranium isotopes, gradually increasing the concentration of uranium-235. Thousands of them connected in cascades form the core of Iran's uranium enrichment operation. Now the pieces fit together. The trail pointed to Natanz, Iran's main uranium enrichment facility. Natanz had been at the center of an international dispute since its existence was publicly revealed in 2002 after years of undeclared nuclear activity. Iran maintained that its program was peaceful, but uranium enrichment is dual use. It can produce fuel for civilian reactors, or at much higher levels, materials suitable for nuclear weapons. By the mid-2000s, inspections, negotiations, and sanctions had failed to stop Iran's expanding enrichment capacity. Later reporting by the New York Times describes Stuxnet as part of a covert U.S.-Israeli program known as Operation Olympic Games, although neither government has officially acknowledged responsibility. At Natanz, the centrifuge motors normally ran at around 1064 Hz, or about 63,840 revolutions per minute. During one attack sequence, Stuxnet pushed them to 1,410 Hz, about 84,600 revolutions per minute, for roughly 15 minutes. Weeks later, another sequence could drop them to just 2 Hz, around 120 revolutions per minute, before accelerating them again. Changing their speed forced the rotors through resonance frequencies, where vibration became especially dangerous, increasing mechanical stress and the likelihood of failure. That was the point. Not one obvious explosion, but failures that could look like unreliable equipment rather than sabotage. So, did Stuxnet work? IAEA, the International Atomic Energy Agency, reported that roughly 1,000 centrifuges were removed and replaced during a period of poor performance at Natanz, and Stuxnet likely contributed to those failures. But the effect was limited. The attack did not destroy Iran's nuclear program, and enrichment continued. Estimates vary on how much time Stuxnet actually bought, but any delay appears to have been temporary. Its bigger impact was proving that malware could move beyond computers and cause real physical damage. Before Stuxnet, malware was mostly associated with damaged computers or stolen information. Stuxnet showed that malicious code could reach beyond the computer and affect physical equipment. Natanz was air-gapped, with its critical systems isolated from the public internet. Stuxnet was designed around that limitation, spreading through trusted computers, removable media, and engineering systems. Attackers didn't need direct access to the machine if they could compromise the computer trusted to program it. Stuxnet proved that software could become a physical weapon, and once that possibility was out in the world, there was no putting it back. If you enjoyed this story, subscribe for more tech stories told in under 10 minutes. I'm Isa, and I'll see you in the next one.